Welcome back, Nature and Code. We're in chapter 6. We're talking about the matching allele model here that we're implementing. And so far in our code, we have implemented these functions here, or this one function rather, initialize frequencies, where we initialize the host and the parasite frequencies. And then we set up this loop here where we're pushing the new host frequencies and parasite frequencies after host and parasite selection. But what we need to do now, of course, is to implement these functions. So let's think first about how these functions should work. So we have previously seen when calculating fitnesses or frequencies of genotypes in the next generation based on fitnesses, what we have done was basically this. We have basically assumed that the frequency of some genotype would be in the next generation would be its current frequency multiplied with some fitness value, W. And now if we have multiple fitness values like this and multiple frequencies, then it might very well be that after we've multiplied these, after we've calculated this product between frequencies and fitnesses, the new frequencies won't add up to 1. And that's why we have to normalize it by this W bar. And we're going to use the exact same logic here. So in our case, we'll have 4 frequencies that we will need to calculate. Now, let's take a look at the host A1. Okay, so its frequency, I'm going to call FH1, in the next generation will be its frequency in the current generation times its fitness. And then again, divided by this W bar, this normalizing factor. Now, the key here is also to realize that this value, and that's a key difference between what we've done in the earlier videos of this chapter and this video. This value is not fixed. That is what frequency-dependent selection is. It is not fixed. The fitness value here of this host depends crucially on the fitness of other players. And in this particular case, it depends on the fitness of the parasite frequencies. Think about it like this. As the host A1, you can run into 2 parasites, right? You can run into parasite A1, and you can run into parasite A2. And you will do so with the probability that equals their frequencies. So frequency of P1, frequency of P2. So say, let's say there are 20% A1 parasites. Well, the chance, of all your interactions, on average, you will run into A1 parasites with a likelihood of 20% and into A2 parasites with a likelihood of 80%. And so, there are these 2 possibilities, and we simply have to add those up to get the fitness value of, a particular genotype. So in our case, we're interested in this WH1 here, WH1. So now that is simply this product here for, the parasite P1 multiplied by the fitness that the host gets when it interacts with P1. And we know this from our matrix. And then the other part from this term comes from, this host running into P2, which happens with frequency P2, and then multiplying this with the fitness of host 1 interacting with parasite 2. So that is this fitness here. To go back to concrete numbers, so this could, for example, be 0.2, and this could, for example, be 0.8. Now, what is the fitness of the host 1 when it interacts with parasite 1? Well, we've seen before that means, the alleles match, so it's an infection, so that's bad news for the host. So this is going to be 1 minus SH, and this is going to be 1, because if the parasite 2 tries to infect the host A1, it won't be able to infect, and the host will have the maximum fitness. So this is how we calculate this. And so what we need to do is we simply need to express this this idea here in code. Because once we've calculated this, then we can simply multiply it with its current frequency. And then we do this for the 4 genotypes, and then we add those up together. This is now our W bar, and this will be now our normalizing factor. So let's go ahead and do exactly that. So I'm going to go over to my code, and I'm going to implement here this function host selection. Let's start with host selection, because the exact same logic will apply to the parasites. Host selection. So I will set up a loop now where I go through all the hosts. In this case, I just have 2, but I'm still going to set up a loop. So I'm going to say for var I equals 0, I smaller than host frequencies length, which in our case will be 2. And then of course I equals I plus 1. Okay, so what do I want to do for each host? Well, for each host, first of all, I would like to calculate this host fitness. So I'm going to say var host fitness, and now I need to calculate this. And I'm going to do this by basically, first starting by initializing this at value 0. And so now, as you've seen on the slide before, I now need to go through the parasites, because a host can now interact with each parasite. So I'm going to have another loop here. And so in this inner loop, I'm going to use II as usual. And then II is smaller than parasite frequencies length, because I'm going through each parasite. And again, in our example here, this will be 2. And then II equals II plus 1. Good. So now I can simply say, well, host fitness is, what I had before, plus, so I'm just going to create this sum of this product, right? W of the interaction, the fitness of the interaction in this matrix, and the frequency. So to do that, I'm just going to, write an extra function here. I'm going to call this get WF. Okay, so this is sort of the, it means get the product of this W and this F. And I'm going to pass in these indices here so that, this function knows which of the host genotype and which of the parasite genotype I mean. So let's go ahead and implement this right away. This is actually very simple. So function get WF of 2 possible genotypes, and again I'm just going to have here the corresponding indices of the array. Now, this is a matching allele model, so I can simply say, well, if they match, right, if they're both the same ones, so if I equals II, then I will have to, I will have to multiply the parasite frequency of this II parasite with 1 minus sh, because if they match, the host gets in. So I will have to say return 1 minus sh times parasite frequencies II. And if they don't match, then there's not going to be an infection. So the fitness of the host will be 1, and I'm going to multiply this with the frequency, because that's exactly what this function should do. It should give me the product of the fitness, which is either 1 minus sh or 1, depending on whether they match according to our fitness matrix, times the frequency, in this case, of the parasite. Okay, so let's go ahead and finish this. Now, I will have this exact same function here, slightly different for parasites and for hosts. So I'm just going to rename this function here to get host WF, and consequently here where I use it, I need to say get host WF. Okay, now I want to show you just one trick that makes your JavaScript a little bit more compact, even though this is perfectly legitimate. Sometimes when you have a simple if-else like this, you can simplify this with the so-called, with a new operator, and that new operator is called the ternary operator. And it looks like this. So you would here say, instead of these lines here, you would simply say return. And now here's the ternary operator. We would say, does I equal II? Question mark. If it does, use this value here, 1 minus sh. If it doesn't, and here notice the colon, simply use 1. And then I'm going to multiply this here with the parasite frequency. So let me take the parasite frequency here. Okay, so this line is equivalent, exactly equivalent to these lines. And here, this is the ternary operator. So it's a combination of a question mark and a colon. And the way to read this is quite simple. You have a condition. Then if it's true, after the question mark, you use the term if this condition is true. Otherwise, you use the term after the colon. And this is, of course, exactly what we have here, right? If I equals II, return 1 minus h times parasite frequencies II. Else, return 1 times parasite frequencies II. So this is the ternary operator, and when you have a very simple if-else like this, you will often want to use this to make things a little more compact, which you don't have to, but I want you to be aware of that, and I'm going to use it here. So this function has just now simplified quite a bit. Okay, so we're almost done. So what do we have now? So after this loop here, we have now calculated our host fitness. So this, just as a reminder, what we've just done here in this simple loop here, okay, is basically calculated this term here. Okay, it's the sum of these products. It's the sum of these products of the fitness and the frequency. That's exactly what we have here. It's the sum of these products here, W times F. Okay, so we have calculated this now. And now, as we've seen, well, now that we have this current host fitness, for example, WH1, what do we need to do with it? Well, we need to multiply it with the current frequency. So let's go ahead and do that. So quite simple. So host frequencies of the ith element is now whatever we currently have, so the current host frequency of the given genotype, times exactly this fitness that we just calculated. Oops, and I have a typo here. This should, of course, be a double S. Okay. All right, so this line now corresponds to this multiplication. And what we need to do now, and we've actually already done this, we need to do this for both the hosts. And we've already done this because we have this loop. So now we need to calculate this normalizing factor, which is simply the sum here of these products for both the hosts. So let's go ahead and do this. We currently don't keep track of that. So let me add this here and call this sum host frequencies equals 0. And so here after we calculated this new product of the old frequency and this calculated fitness given the current parasite frequencies, now we need to add this to what we already have. So sum host frequencies plus host frequencies. And so now when we're done with the loop, with the outer loop here, this sum host frequencies will now just be the sum of the new host frequencies that we calculated. And so this will now act as our normalizing factor. So all that's left to do for us now basically is to normalize these, because now these two host frequencies wouldn't add up to 1. So let's just go ahead and do this. Once again, simply set up a loop for the host frequencies. Okay, for var I equals 0, I smaller than the host frequency's length, I equals I plus 1. Okay, simply now say host frequencies I equals, whatever you have there. Oops, that should be not a capital I. I've got caps lock here, sorry. So host frequencies I, whatever we have, divided by this normalizing factor, which is our sum host frequencies. Okay, and that's it. Now it looks a bit like a beast, but it's actually, if you spell it out on the slides and you calculate exactly what those fitnesses are, then it's fairly straightforward to implement this. So once again, what we do is we simply, for each host, we calculate this term, the current host fitness, given these parasite frequencies. Then we multiply this with the current frequency of the host. And we add all these products, which are the new frequencies, we add them up. And this gives our W bar, which is our normalizing factor. And we normalize it, and then we have our new host frequencies, and they add up to 1. So this is host selection. Now parasite selection is exactly identical. So go ahead and copy this function here. Put it down here, and now you just need to rename these functions. So this should be called parasite selection. And now, of course, you go through the parasite frequencies. So here you have some parasite frequencies. Now here you need to while through the parasite frequencies. Then you set up this variable, parasite fitness. And now for each parasite, you go through each of the host frequencies and you calculate the parasite fitness based on these host frequencies, right? For the parasite, it's the exact same logic. So parasite fitness will be parasite fitness plus get, and now here we say parasite WF. And then once again, now that you've calculated these fitnesses, you can simply say parasite frequencies I equals parasite frequencies I times, the fitness of the parasite. And to keep track of this normalizing factor, you say here sum parasite frequencies equals sum parasite frequencies plus parasite frequencies. Okay, and then you normalize. So again, you go through all parasites, and then you say parasite frequencies I equals parasite frequencies divided by sum parasite frequencies. So the exact same thing, except you now replaced host with parasite and you replaced parasite with host. And so this function is now called get parasite WF. And there's one thing here we need to change, because remember here the fitness is actually flipped, right? So if I equals II, which means we have matching allele, then we need to return 1 times host frequencies, because this is the fitness of the parasite. And if it's matching allele, that means there's an infection, and thus the parasite has the maximum fitness. However, if they don't match, then the fitness of the parasite is 1 minus SP, as according to our matrix. And this is it. So you should now be able to save this and reload it in your, or load it rather, in your browser. So let's go ahead and load this real quick in our browser and see what happens here. So open file, chapter 6, coevolution, open. Okay, nothing happens, which probably means we made a mistake somewhere. Let's see. What are we missing? Let's just go back to the code real quick. I just want to make sure. Oh yes, of course. Okay. We are trying to draw the lines here, but we actually haven't implemented our draw line chart function, or we haven't copied it over. So what I'm going to do is I'm just going to open a previous example. Let's say, delta P versus P, just some code that has the drawing code here. I'm going to copy the drawing code. You can also copy it from the website. Okay, this function draw line chart, and I'm going to put it up here as before. And finally, I also need the script tag here that loads the D3 library, which I copied from the D3 web page. And I'm going to put this in my head. Okay, so now save it, go back and reload it. And here is the dynamic. And if you reload this, you can see this looks slightly different depending on the initial condition, it turns out. But these are now the 4 frequencies, and you can see this is completely cyclical coevolution. So, as one of the genotypes goes up in frequency and the other one goes down, the antagonist will then chase that frequency and increase one of its frequencies and decrease the other of its frequencies. This is exactly what we would predict in this antagonistic coevolution, the cyclical dynamics. And as you can see here, that's exactly what happens here. So we can talk a little bit more about these dynamics, because there's some interesting aspects here about those, and we'll do that in the next video. So see you in the next video.